Hello viewers, my name is Abongile Mbushang from Ulwazi High School. Welcome to the ECDoE broadcast studio. Today's lesson is about vertical projectile motion. Let me take you through to the slides. On vertical projectile motion, we will deal with the concept that is the projectile motion, equations of motion, the projectile motion, the projectile graphs, and more projectile graphs that is now from different scenarios. As you know, that is we're being guided by this this document. We call that examination guideline. So the definition that are expected that is on VPM are defined. That is what is free fall, and also define what is a projectile. So these definitions are more or less the same, but now the projectile there is an object which is given an initial velocity, but a free fall here is a motion. This one, so that's the difference between the two. That is on those definitions there. So the other one is object, then the other one is motion here. Okay, so we take that this definition exactly as they are from the examination guideline. Okay, so this guide is giving us now that is a scope towards the final examination there on what we're supposed to know. So it's saying now that is we must know the equations of motion there to determine a position, a velocity, a displacement of a projectile there at any given time. Okay, and also we must be able to sketch that is a position versus time graph, and also a velocity versus time graph, and also an acceleration versus time graph then for a free falling object, and also for an object that is thrown vertically upwards, and also for an object that is thrown vertically downwards, and also for bouncing object here. Okay, so also even if we are given the graphs, that is a position versus time graph, and also velocity versus time graph, and also acceleration versus time graph, we must be able to determine the position, and also the displacement, and also the velocity or acceleration at any given time. Okay, so the prior knowledge here that is on mechanics, that is the Newton's laws from grade 11, acceleration as soon as from grade 10, net force from grade 11, displacement, velocity, the equations of motion then, they are from grade 10. We introduced them from grade 10, then the free body diagram from grade 11, then the graph of motion also from grade 10. Okay, so let's move now. Okay, so the lesson objective here, a learner now must be able now to know and define, that is a free fall, must be able to define a free fall, must be able to define that is a projectile motion, and also describe a motion. Then also you must know that is the reference point. Then also use the equations of motion to calculate acceleration, calculate velocity, calculate the displacement, and also calculate the time. And also you must be able by the end of this lesson to draw a graph of motion then for a position versus time graph, acceleration versus time graph, velocity versus time graph then. And also, learners, you must be able to interpret them, the graphs, if you are given a one. Okay, let's move to, so that now we can have a clear guide of what is expected here on. So now these are the concepts of projection here. That means now I will look at this one from different scenarios. Okay, so the first scenario that is I will look at is of an object that is being dropped from a certain height above the ground from rest and allowed to fall freely. Okay, also note that the sign of G now is not yet a big issue on that scenario. Okay, so that's the first scenario that is will take us through. Okay, let's move to that first slide then, to that first scenario. Okay, on this first scenario, for a dropped object. Okay, so if now we're dealing now with a dropped object here, the word that is dropped there means something that is a science concept. This one, that means now the velocity here is equal to 0. Okay, so this one is dropped then at a certain height above the ground. Okay, so that means now if we're having that is on top of the building, maybe this object is dropped from the top of the building, then it goes straight downwards to the ground. Okay, so if it is dropped, then you must know there that is the initial velocity there is 0. Okay, then also if we ignore the effect of air resistance, or air friction, then we're going to have now only one force that is going to be acting there, that is the gravitational force. So that means now as the ball, okay, learners, now let's go to the scenario number 1. So on scenario number 1, then an object then is being dropped. So if now the object there is being dropped, that is now is dropped from the certain height. There is no way that is now you can drop a ball that is already on the ground. So that means now if the ball is dropped, that means now this ball is from a certain height, then it goes down. It goes down then. Okay. Okay, let me use a different pen. Sorry about that. Okay, so if it is dropped there, that means now it's from a certain height there. Then who dropped them? We must know that if the ball is dropped, then the initial velocity then is going to be given as 0. Okay, so and also if it is dropped then is from a certain height above the ground, because we cannot drop a ball from that is already on the ground. Okay, and also if we ignore the effect of air resistance here, then we're going to have now only one force that is going to be acting. So if now there's one force that is acting is force of gravity, then the acceleration due to gravity there is going to be given as 9,8 then. Okay, then also the only force acting there is the force of gravity. That means now that one is a conservative force. Okay, again, as the ball moves, let me use different pen. As the ball moves from upwards to downwards here, the velocity, you must know that, let me make this pen a little bit lesser, or let me, okay, so you must know that the velocity here is decreasing. Sorry, the velocity is increasing as object is going downwards, always there. Okay, so the reason now the object now is increasing in terms of the velocity then is because the velocity is going downwards, also this v is going downwards, and also this g, the gravitation due to acceleration, they are going in the same direction now. So every object that is going downwards then their velocity there is going to increase them until they reach what? The ground. So for this one now is from, that is 0 since the ball is dropped, then as it hit the ground, that now is going to hit the ground at a final velocity that is not 0. That velocity there is going to be more than 0 or greater than 0 from then. Okay, then now let me take you through to the first scenario. That is now an object that is being dropped now from a certain height there. So the word that is dropped there, we must note that the velocity then is 0, or the initial velocity there is given to be 0 if now the object is being dropped. So the initial velocity is 0. Okay, and again, an object there cannot be dropped if it is on the ground. That means now an object, in order to be dropped, it must be at a certain height then. Okay, so on that one, the ball is dropped from a certain height above the ground. And also on our problems here, we ignore the effect of the air resistance. So if we ignore the effect of air resistance, then the only force that will be acting there is going to be now the force of gravity then. Okay, so if now the force of gravity is acting there, then it's going to make now the gravitational acceleration there to be 9.8 meters per second downwards, then is always going downwards. That is our G. Our G is always going down, okay? So if there's only one force acting on an object, then that force there will become what? A net force, okay? So now on this problem that we're having, or on this scenario, then let's say now the object there is being dropped from a certain building. Then one or two things that we must note, then the initial velocity is 0 because it is dropped from a certain height there, okay? Then when the ball reaches the ground, we must know that the velocity there is going to be greater than 0, okay? So since it's greater than 0, because as the object is going downwards here, we must know that the velocity increases there every time, okay? So since the velocity increases there, it is because that the G, the gravitational acceleration there, is also going downwards. So the velocity as the object is going down and the gravitational acceleration there, they are going in the same direction. So if they are going in the same direction now, then the object is going to speed up, okay? So hence we're saying now, as the magnitude of the velocity of the therefore increases them from an initial velocity of 0. So hence we're saying now, the final velocity there cannot be 0. It's supposed to be greater now, okay? Let me take you through to the next slide. Okay, so now let's look now on the problem that we're having here, that is for an object that is being dropped from a certain height, okay? So they're given here that is now a ball is dropped from the top of the building that is 20 meters high. So that means now here we're given our delta y, okay? So we ignore the effect of a resistance. So if we ignore the effect of resistance, then we must know now our object there is on free fall. Now we must know that is our object is on free fall there. Then the only force acting there is gravity, okay? So now let's look here. That is, once we're having the most important part about this topic here, we must now the choice of direction there. So remember, the choice of direction there is entirely to you. Whether you choosing that is up is positive or down is positive. But on our case here, the object is going downwards. So if the object now is going downwards here, that's the only motion that we're having there, that is downwards, okay? So it is very much wise now that is we take that is put down as positive on this case, because now everything is going downwards, okay? So everything that is going to go up now will be negative. So now the choice of direction first, and also, okay, the meaning of dropped, so, or release. So if sometimes they can use also the word that is release. So they mean almost the same thing there. That is dropped, in that now the initial velocity there is given to be 0, as I alluded first there. Okay. So now let's look again. If we're given the, let's say now the time taken now to hit the ground. Okay. So if now want to calculate the time taken to hit the ground, we must also gather what we call now a data in order for us now to be able as to choose the equations of motion Z, okay? So from here on our data, on the statement, they were given this guy, that is the height. So that is now delta y there is given to be, okay, delta y is given to be 20 meters, okay? So on this case now, that 20 meters is positive because now this one is going to be our initial, okay? So if now this one is our initial position here, then the height of the building now is down. Then that now is on this side from the initial position there. So if now is down, that means now that delta y there is going to be positive, okay? Then also, we know that our initial velocity then is given to be let me fix my slide here. Okay, we're good to go. Okay, so our initial velocity then is given to be 0. Okay, and now that we ignored, that is the effect of a resistance here, Now that we ignore the effect of air resistance, then we must know that our G is given to be positive 9,8, because remember now, we said that now this one is always going downwards here. Okay, so now what do we want here? We want now our delta t, that is the time, that's our unknown that is want to calculate here. Okay, so now once we know three things here, now it's going to be sufficient for us now as to be able to calculate whatever variable that is we want to calculate. Okay, so as we're looking here, that is we're having those equations of motion here. The first one, v initial, sorry, v final, v initial plus at. Then the second one is v final squared, which is equal to v initial squared plus 2a. Okay, the third one is delta y, which will be given as v initial delta t plus half a delta t all squared. Okay, then the fourth one is delta y, which is equal to v initial plus v final all divided by 2, then multiply here by delta t. Okay, so we're having now all these four equations of motion here. So now that there are four, each and every equation of motion here is containing 4 variables. So hence I was saying that now you need to know 3 things here. Now on our equation here, we know our delta y, we know our initial velocity, and also we know our gravitational acceleration here. And as you are looking here, that is on these equations of motion here, there's only one equation here that is containing, that is our v initial here, of which is now this one is going to be our third equation here. That means now we can be able to use our third equation to calculate the time, because now the delta y is here, that we know, the initial velocity that we know is also here, and also that acceleration there is also there. Okay, so now we can be able to calculate our time here. Okay, let's do that now. Okay, so we're having delta y, which will be given as v initial delta t plus half g or a t squared. Okay, let me use here delta. Okay, our delta y there is given as 20 meters. Okay, then our initial velocity here is 0 multiplied by delta t, the one that we want, then plus half into acceleration here is positive, so it will be 9,8 and delta t squared. Okay, so if we now want to simplify that, on this side we're still having 20, which will be equal to 0 times at any variable or any number is going to give us 0. So half times 9,8 is going to give us 4,9 delta t squared. Then we divide both sides by 4,9, then both sides 4, so if we're dividing that is 20 by 4,9, then we're going to get now that is delta t squared will be 4,08. Then if we're taking square root of that, our final answer will be given as delta t, which will be equal to 2,08 seconds here. Okay, so that is the time. Okay, delta t squared is given to be 4,08 then. Okay, so we take the square root both sides. Then as we know that the square root there is plus or minus here. Okay, but now we know that the time now cannot be negative. So the square root then of 4,08 there is going to give us, that is the time that is 2,08 seconds. Okay, so from there, so we know that the time now for the entire journey there is going to be, or before it hit the ground, is 0,28 seconds. Okay, now let's go now to the another concept here. Then the concept is saying now we must calculate now the velocity when the ball hit the ground. Okay, then also we must create our data, and on our data now we know that is we had first that is 3 variables. Now that we've calculated the time, now we're going to have now 4. Okay, so on this now we'll be having the initial velocity, which is 0. Then we're having acceleration, which is 9.8 meters per second squared. Okay, and also we're having that is delta y. Delta y is given as 20 meters. Okay, then we're having also the delta time, the time that is calculated for the ball to hit the ground. So that is 2.08 seconds here. Okay, then now we want now the final velocity of which the ball hit the ground. Okay, so now we can go to the first equation that say V final is equal to V initial plus A delta T. Okay, so we want now the final velocity with which the ball hit the ground. So our initial here is 0 as the ball was dropped, plus then our acceleration is 9.8. Then our time here to hit the ground is 2.08 seconds. Okay, so if you multiply 9.8 by 2.08 here, you're supposed to get 19.80 meters per second. Here. Okay, so the velocity is positive since now the motion is downwards. Okay, then now let's go now to the in drawing the graph on this scenario. The one that is saying now we must draw, that is the position versus time graph for this scenario. Okay, so now if we're to draw a graph, let me use a different color. Okay, then if we're having that is the position P versus T, that's position versus time graph, whereby on our y-axis here we're having position in meters, then on our time axis here we're going to have now that is the time in seconds. Okay, so now for our object then, remember the object now was dropped from a certain height of 20 meters of a certain height 20 meters to the ground. Okay, so now at this position here our ball was from 20 meters. Okay, so it goes straight downwards until it hit the ground. Okay, so it hit the ground and at the time that is 2.08 seconds. It hit the ground at 2.08 seconds. So that's how the graph, our graph supposed to look like. That's how our position versus time graph supposed to look like for this scenario. Okay, so now another concept here is say now we must be able to draw a velocity versus time graph for the same scenario. Okay, so if we were to do now that is the velocity versus time graph. Okay, so learners must note also that is on position versus time graph. Then this graph now it contains a curve. That means now as the ball is going downwards or moving upwards, then it's changing its position then. So it's going to give you that is now the curved graph. Okay, so once it changes the position, definitely the velocity now is going to be changing. Okay, then now let's quickly go to them the one of drawing the velocity versus time graph. Okay, so a velocity versus time graph. So if we're given like that, so let me say V versus T. So whereby here we're having the time in seconds, then on the y-axis we're having velocity. We're having velocity in meters per second. So we know that now our ball was dropped. So if now the ball is dropped, we note that now the velocity is 0. So that means now our graph is supposed to start where the velocity is 0. Okay, and also remember that is now we took that is upward as positive. Sorry, we took downward as positive. So this one is a positive side of the positive side. Then this one is a negative side in terms of the velocity. So that means now our graph need to lie on this side as it goes downwards. Mean that now it must lie on the positive side, starting from 0. That is the initial velocity is 0. Okay. And also we know that now as the object that is going downwards, the velocity increases here. So that means now on the graph here, it's supposed to start at 0, then it increases straight to, okay, to that, then the final velocity that we got there, it was 19,8 then. It was 19,8 then, okay? So now from this graph here, also the time it took to hit the ground, it is 2,08, okay? So the problem that the learners are doing now on this graph, okay? So this graph here is going downwards. So that now you need not to take now this one as literary. Now that the object is going down, then you want the graph also to go down. You see, remember you are talking here about what? About the velocity, okay? So the velocity, we said that as the object is going downwards, the velocity increases. Mean that now as the velocity increases here, then that velocity they're supposed to increase. Mean that now from what? From 0 up until it reaches ubani, that is a 19,8. Okay, so that now the velocity is increasing there in that positive direction that you have chosen there. You took that downward as positive there. Okay, so that is the graph, that is the shape of the graph for velocity versus time graph. Okay, then now if we're moving now to the one that is now the acceleration versus time graph. The acceleration versus time graph. On acceleration versus time graph, on acceleration versus time graph, we're going to have now, remember, as the ball is going downwards or upwards, the acceleration is constant, is 9,8 meters per second squared. So if I can have here 9,8 positive 1, this side I'm having 9,8 and negative 1 here. Okay, so remember, we took that is down as positive. So if we took down as positive, then that now our graph is supposed to lie on this side also, okay? So that means now this one is supposed to be just a straight line graph there like that. That means now as the time is changing here, but now the acceleration then is not changing there, okay? So, okay, up until it reaches, that is the time, which is 2,08 there. So that's how our acceleration versus time graph supposed to look like for this particular scenario. For this particular scenario there. Okay. So now again here, it says now the last bullet here, that's now the interpretation now of velocity versus time graph. So now on that velocity versus time graph, on this one, okay, in terms of the area between the time axis then and the graph and the gradient. Okay, so now when we talk of the this graph, when we're looking at this graph here, we'll remember that now our gradient there on maths is y2 minus y1 divided by x2 minus x1. Okay, so from there, from that, we must know that our gradient, let me use G for a gradient then. On y-axis here, we're having what we call now the velocity on y-axis here. That's the velocity that we're having divided by the time. Divided by the time, okay? So that is now on the x-axis here, we're having, that is the time, okay? So now, remember that is now a change, okay? It's supposed to be a change here as also a change. So a change in velocity, okay? A change in velocity, we're saying now a rate of change in velocity. That one is given to be what? An acceleration. That means now a gradient of this graph here supposed to give you an acceleration here. That is what? That is 9,8 meters per second squared. Okay, so the gradient of velocity versus time graph is acceleration. Okay, because now it is given as a change in v divided by the change in time. So as you know from the definition of acceleration, it is a rate of change in velocity. Okay. Then if we are to move now to an area, if we want to move now to an area below the graph, we want to move to an area below the graph. So the area below the graph there is giving now a nice shape of right angle triangle there. So an area of a triangle there is given as half base times height. Okay. So now, okay, so if we're looking at the base, so the base there is given as the time. Okay, is given as the time. X is here. Okay, then the height there is given as what? As the velocity. Is given as the velocity. Okay, so now you'll note that now velocity is equal to the change in x divided by the change in time, or is the rate of change in displacement. So if you are to cross multiply here, you are going to get change in displacement is equal to, that is velocity multiplied by the change in what? By the change in time. Also, this is what is giving here. Okay, so that means now the time times the velocity then is supposed to give us what? Then change in displacement. So that means now the area below this graph here is giving us what we call now what? A displacement then. Is giving what we call now a displacement. Okay, so I think now we're fine with that. We've come to the end of our lesson. You can leave your question on comments. Don't forget to leave the name of your school so that you can shout out. Please share, recommend, subscribe on our YouTube channel. We'll see you on the next lesson there, that is on the second scenario. Thank you for watching.